Over the past 20 years, you've been told at least 9 times that a second Earth has been found. 9 times. In different words. Earth's twin, Earth's cousin, a planet that could support life. Headlines, magazine covers, broadcasts. And every time you probably felt the same thing, a brief jolt of something big. We're not alone. There's another home, somewhere to go. Now take a look at what's left of those 9 planets. Gliese 581c, 2007, the first planet seriously called potentially habitable. Today, we know it almost certainly gets so much energy from its star that a runaway greenhouse effect has taken hold. This isn't a second Earth, it's a second Venus. Gliese 581g, 2010, the planet declared the perfect candidate, right in the middle of the habitable zone. The problem is, when the data was rechecked, no one could see it anymore. The signal was indistinguishable from the star's own noise. So this planet probably doesn't exist at all. It never did. Kepler 22b, 2011, the first planet in the habitable zone found by the Kepler telescope. Radius almost 2.5 times Earth's. At that size, it's most likely not a rocky world at all. It's a mini Neptune. A ball of gas and water with no surface to stand on. Kepler 186f, 2014. Now this one is more interesting. It's actually Earth-sized, and it's actually in the habitable zone, but it's 500 light-years away. Its star is a dim red dwarf, and we know absolutely nothing about its atmosphere. Zero. We don't know if there's air. We don't know if there's water. All we know is that it exists, and it's roughly the right size. That's it. Kepler 452b, 2015, dubbed Earth's cousin, and it was probably the loudest headline of the decade. Then, in 2018, a paper came out that cast doubt on its very existence. The signal is too weak. Maybe there's nothing there at all. Proxima b, 2016, the closest one, just 4 light-years away. A dream. Except its star, Proxima Centauri, regularly unleashes flares so powerful that in a matter of minutes it blasts out energy capable of stripping the atmosphere off a planet orbiting that close. One such flare was recorded in 2019. The planet got a radiation dose that makes talking about a calm surface life pretty difficult. TRAPPIST-1, 2017, 7 Earth-sized planets around a single star, 3 or 4 in the habitable zone. It was a real sensation, and honestly, it's still the best we've got. Then, the James Webb Space Telescope, the most powerful instrument humanity has ever launched into space, looked at the inner planets of that system and found no thick atmosphere. Looks like bare rock, scorched bare rock. That's the list. 9 promises, and not a single home. And you know what's most interesting? Usually, this is where you get the speech about how we're just not looking hard enough, that our telescopes are still too weak, that we just need to wait, that any day now, one more mission and we'll find it. The real one. The one. I want to offer you a different thought. We won't find it. And it's not about the telescopes. It's because we're looking for the wrong thing. We're looking for a place, a planet, a point in space with a specific set of characteristics, the right size, the right distance from its star, the right temperature. We've drawn up a checklist, and now we're wandering the galaxy, holding it up against everything we find, like a shopper with a tape measure in a furniture store. But Earth isn't a place. Earth is a story. It's 4.5 billion years of events, each one of which could have gone differently. A collision that should never have happened, a moon that shouldn't be there, a core that still hasn't cooled down, while all the neighbors cooled off long ago. A crust that somehow didn't freeze into a single shell, but split into plates and started breathing. A catastrophe where life poisoned its own planet and nearly killed itself off. A single random meeting between 2 microbes that, as far as we can tell, happened exactly once in Earth's entire history. And 5 mass extinctions, each one wiping out nearly all life, and each one somehow leaving just enough to start over. Remove any one of these episodes and you wouldn't be born. There would be no one to watch this video. There would be no one to watch anything at all. You don't find something like that in a snapshot. You can't measure it with a light curve. A planet like that can only be lived from beginning to end, all 4.5 billion years, step by step, without skipping a single turn. That's what we're going to talk about today. We'll walk the entire route, every twist and turn. And by the end, you'll understand why the question, "Where's the second Earth?" is the wrong question. And why the only habitable planet humanity has ever found is already found. You're standing on it right now. But to get that, we first need to figure out where this checklist even came from and how empty it really is. Let's start with the most important word in this whole story. The word you've heard 100 times, and that, chances are, doesn't mean what you think it means. The habitable zone. Sounds great, doesn't it? Habitable, right there in the name. Like it's a belt around a star where you can just set up shop. In reality, the definition is a lot more modest. The habitable zone is the range of distances from a star where liquid water could theoretically exist on a planet's surface, provided the planet has a surface, provided it has an atmosphere with the right pressure, provided that atmosphere hasn't escaped, provided the planet is even rocky in the first place. That's a lot of provideds, and only the word habitable makes it into the headline. But let's not even talk definitions. Let's talk practice. I've got a very simple test for you, and it works better than any argument. In our own solar system, there isn't just one planet in the habitable zone. Depending on how you count, there are 2 or 3. Earth, yes, of course. Mars, by most calculations, it's there too. It's on the outer edge, but it's in. And Venus, it's right at the inner boundary, barely inside, and by some estimates, still within. 3 planets, 1 zone, 1 star. Now look at what those worlds are like. Venus, surface temperature, 465 degrees Celsius. That's hotter than Mercury, which is twice as close to the Sun. Surface pressure, about 92 Earth atmospheres. Imagine diving 900 meters into the ocean. Not 900. Any unprotected tech dies there within minutes. The Soviet Venera probes landed on that planet and transmitted data for less than 2 hours. Then they were just crushed and melted. Sulfuric acid falls from the sky. A day there lasts longer than a year. The planet spins backwards compared to all the others. This is a planet in the habitable zone. Now, Mars. Average temperature, -60. Atmospheric pressure, less than 1% of Earth's. So low that liquid water simply cannot exist on the surface. It either freezes instantly or evaporates instantly, skipping the liquid phase entirely. Surface radiation is unfiltered. The soil is soaked with perchlorates, salts that are toxic to most Earth-based biochemistry. This is also a planet in the habitable zone. So there you go. Out of 3 planets in that magical life-friendly belt, one is a scorching hell under acid clouds, the second is a frozen radioactive desert, and only the third, the one under your feet, actually works. 33%. And that's only because we got lucky with our sample. That's what the word habitable in a headline is really worth. If an alien astronomer from another star aimed their telescope at the solar system, they'd see 3 rocky spheres, roughly the right size, roughly the right distance from a yellow star. They'd write a paper. They'd probably tell their colleagues, "Look, great system, 3 candidates in the habitable zone, high probability of life," and they'd be exactly 1/3 right. And if their priorities were off, they'd point their instruments at Venus, see a thick atmosphere, and get even more excited. There's an atmosphere. There's carbon dioxide. There are clouds. Perfect candidate. They'd be completely wrong. Now, keeping that in mind, mentally go back to that list we started with. The Keplers, the Glieses, TRAPPIST-1. Because we know 1,000 times less about those planets than our imaginary alien knows about Venus. By the way, if you like this kind of breakdown, no sugarcoating, no scientists think there might be oceans, hit subscribe. I genuinely need to know this format matters to someone, because making it is way harder than just rehashing a NASA press release in a smooth voice for the 100th time. Okay, there's another criterion: size. Earth-sized planet is the second most common phrase in those headlines, and it's almost as meaningless. Here's the thing. When a telescope finds a planet using the transit method, catching the moment it passes in front of its star and the star dims just a tiny bit, we measure exactly one thing: how much the brightness drops. From that dip, we calculate the planet's radius. That's it. We don't see the planet. We don't see it at all. We see a star flicker by 1/100%, and from that, we infer the size. Now, here's the kicker. There's this thing called the radius gap, or the Fulton gap. It was discovered once we had enough statistics from thousands of exoplanets. Turns out, planets in the galaxy aren't evenly distributed by size. There's a clear canyon. Planets with a radius between roughly 1.5 and 2 Earth radii are suspiciously rare. Why? Because it appears to be the dividing line between two different types of worlds. Everything smaller than about 1.5 Earth radii is typically a rocky planet. Everything larger than 2 is usually not rocky anymore. These are the so-called mini-Neptunes, a small rocky or icy core wrapped in a thick envelope of hydrogen and helium. Such a planet has no surface in the familiar sense. You can't land on it. The atmosphere just gets denser and denser until it turns into a supercritical fluid. There's no point where your foot hits rock. That moment doesn't exist. And here's where it gets ugly. Kepler 452b, that so-called Earth's cousin, has a radius of about 1.6 Earth radii, right in the gap. Kepler 22b, almost 2.5, way over the edge. So that word cousin in the headline could have been referring to an object with no solid ground at all. And it was. But we're not even at the bottom yet, because radius is only half the information. To figure out what a planet is made of, you also need its mass. Knowing both, you can calculate density, and then you can say rock, water, or gas. But the transit method gives you zero mass data. For mass, you need a second method, radial velocity, and that only works for stars that are close enough and bright enough. For the vast majority of those second Earths in splashy headlines, no one has ever measured the mass. We know the radius, we know the orbital period, we know the star's luminosity. From these three numbers, we estimate the temperature, making a pile of assumptions about what the atmosphere is like. But we don't know what the atmosphere is like. And from that, from a shadow, from the flicker of a distant point, from three numbers and a stack of assumptions, a headline is born: Second Earth Found. You see the trick? The table we use to search has just two columns, distance from the star and size. And as we just found out, both columns tell you almost nothing about whether it's habitable. Venus and Mars prove that, right here in our own backyard. So what signs should we be looking for? That's where the real conversation begins. Because to understand what truly sets Earth apart from Venus, from Mars, and from all 9 planets on our list, you have to forget about the tables entirely and go back 4.5 billion years to a time when no Earth existed yet. There was a protoplanet. It orbited the young sun, cooled down, and was pretty unremarkable. Just another rocky ball in an ordinary planetary system. And then, something the size of Mars slammed into it. And that collision, the most catastrophic event in our planet's history, was the first thing that made it habitable. It's been tentatively named Theia, after the Titaness who, in Greek myth, gave birth to the moon. We don't know what it looked like. We don't know exactly where it came from. We're not even sure about its size. Different models put it anywhere from something like Mars to something noticeably larger. All we know is that about 4.5 billion years ago, it collided with the young Earth. And this wasn't a glancing blow or a skimming asteroid strike that leaves a crater. This was a merger of two worlds. Think about the scale. Not a meteorite, not a comet, a planet. An entire planet, moving at several kilometers per second, slamming into another planet. The energy of the impact was so immense that a huge chunk of Earth's outer layers didn't just melt, they vaporized, turned into rock vapor. For a time, the planet became a glowing, spinning disk of molten rock and gas, with surface temperatures in the thousands of degrees. If Earth had any crust at that point, any oceans, any atmosphere, they would have been wiped out completely, and they were. Theia's core, according to models, sank down and merged with Earth's core. But some of the ejected material didn't fly off into space or fall back down. It stayed in orbit, a scorching ring of debris and vapor swirling around the battered planet. And out of that ring, in what, geologically speaking, is the blink of an eye, estimates range from a few decades to a few thousand years, the moon formed. Which is exactly why the moon is so strange. Here's the thing. Mars has two moons, Phobos and Deimos. They're basically two lumpy potatoes. Phobos is only about 14 miles across. Those aren't real moons. They're captured asteroids that just happened to wander too close. Now look at our moon. It's nearly 2,200 miles in diameter, over a quarter of Earth's diameter. By mass, it's about 1/81st of Earth's mass. Nothing else in the entire solar system comes close. No other planet drags around a moon of such relative size. Jupiter has Ganymede. It's bigger than Mercury, but Jupiter itself is so enormous that Ganymede is like a speck of dust next to it. Earth and the moon, they're practically a double planet system, a pair. And that's not even the only weird thing. There's something far more telling, though it doesn't get talked about as much. When the Apollo astronauts brought back lunar soil samples, scientists immediately ran isotopic analyses, and they found something nobody expected. The oxygen isotope ratios in lunar rocks are nearly identical to Earth's. Why does that matter? Because every body in the solar system has its own isotopic signature, a kind of chemical fingerprint, shaped by how far from the sun it formed. Martian meteorites are different from Earth rocks. Asteroids are different. Everything is different. But the moon? Not different. The moon is literally made from the same stuff as Earth. And honestly, that's still one of the biggest unsolved problems in planetary science. If the moon formed mostly from Theia's debris, then why the match? Theia should have had its own signature. There are several hypotheses. Maybe Theia formed on nearly the same orbit, out of the same material. Maybe the impact was so incredibly violent that the material from both planets mixed completely in that scorching cloud. Maybe the moon is made mostly from Earth's mantle, not from Theia at all. The honest answer? We don't know. It's an open question, and I'm not going to pretend scientists have it all figured out. They haven't. But for now, what matters isn't where the moon came from. What matters is what it does. Take a spinning top. Give it a spin. When it's spinning fast, it stands upright. Its axis stays steady. Now poke it with your finger. It starts wobbling. Earth is like that spinning top. The planet's rotational axis is tilted relative to its orbital plane by about 23.5 degrees. That's why we have seasons. Half the year, the northern hemisphere tilts more toward the sun. The other half, the southern hemisphere does. Summer, winter. Here's the thing. This tilt barely changes. It drifts, but within a narrow range, roughly from 22 to 24.5 degrees. And the cycle takes tens of thousands of years. That's slow, and that's gentle. What holds it steady is the moon. Through its gravity and tidal pull, the moon stabilizes Earth's axis like a gyroscope. It keeps the planet from tipping over. Now look at Mars. Mars has no proper moon, just those two potato-shaped rocks that do nothing to stabilize it. And Mars's axis behaves completely differently. According to models, over millions of years, it can wander through a range that may span tens of degrees. Some scenarios suggest tilts up to 60 degrees or more. Chaotic. Unpredictable. What does that mean in practice? It means the planet periodically falls onto its side. The poles turn toward the sun and start getting more heat than the equator. The polar caps evaporate, the climate flips, then everything swings back, then it flips again. And we can actually see the scars of this on Mars, layered deposits in the polar regions that look like a chronicle of climate catastrophes, repeating over and over. Imagine this happening on Earth. Every few million years, our planet tips over and the entire climate system goes down the drain. No stable north, no stable south, no predictable seasons. Evolution needs time. Complex ecosystems need millions of years of relatively stable conditions to build themselves up. If everything gets wiped clean every couple million years, life might survive in some primitive form, but it will never build anything big and complex. It never gets a chance to finish. The moon gave us that chance to finish. And now, here's the point I've been building up to. Try putting the moon into the exoplanet search checklist. Doesn't work. We can't see a moon around a planet hundreds of light years away. Technically, it's at the very edge of possibility. There are a few candidate exomoons, debates about them, but no solid, confirmed, widely accepted detection of a large moon around a distant exoplanet. So one of the key factors, without which Earth would probably have no humans, no dinosaurs, no complex life at all, that factor simply isn't part of the list we use to look for a second Earth. We just can't see it, so we don't account for it, and that's why it never makes the headlines. Drop a comment if you already knew about this axial tilt story. I'm curious how widely known it is outside a small circle. From what I can tell, everyone has heard about Theia, but almost nobody knows what it actually gave us. Let's keep going. Because Theia didn't just leave us the moon, it left us a core. Remember how I said Theia's core sank and merged with Earth's? Well, deep in the center of our planet, there's a ball of iron. Actually, two. The inner core is solid. Its temperature is comparable to the surface of the Sun, around 5,000 degrees or more, but the pressure is so insane that the iron stays solid. Around it is the outer core, liquid, molten metal, flowing. And that flow is the most important motion on the planet. Molten metal is a conductor. It moves, the Earth spins, the currents swirl, and that creates what we call the geodynamo, a self-sustaining process that generates the planet's magnetic field. That field extends far beyond the atmosphere and forms the magnetosphere, a teardrop-shaped bubble stretched away from the Sun. Now, why do we need it? The Sun doesn't just shine. The Sun blows. It constantly shoots out the solar wind, a stream of charged particles, protons and electrons, traveling at hundreds of kilometers per second. And that stream slams into anything in its way. Earth's magnetosphere deflects it. Charged particles can't move across magnetic field lines. They get turned and pushed aside. What does leak through along the field lines near the poles, you've seen in pictures. That's the aurorae. Beautiful, and it's literally visual proof the shield is working. You're watching the solar wind hit our defenses and lose. A planet without a magnetic field has no such protection. The solar wind blasts straight into the upper atmosphere and slowly, molecule by molecule, strips it away. And that, it seems, is exactly what happened to Mars. Mars was once different. It had a thick atmosphere. It had liquid water. Dry riverbeds are visible from orbit, and that's not a controversial interpretation. You can just see them. Rivers once flowed there. There may even have been an ocean in the northern hemisphere. Then, its dynamo stopped. Mars is smaller than Earth. It cooled faster, and its core lost the ability to sustain a magnetic field, according to various estimates. That happened about 4 billion years ago. The Mars Global Surveyor Orbiter found remnant magnetization in the ancient Martian crust, a frozen imprint of the field that once existed, like a photograph of a shield that's no longer there. After that, the solar wind got to work. The MAVEN spacecraft, sent specifically to study where Mars's atmosphere went, measured the rate at which it's escaping and confirmed it's leaving into space right now, before our eyes, and in the past, when the young sun was more active, it was escaping much faster. Mars's atmosphere was blown away. Slowly, over hundreds of millions of years. And with the atmosphere went the pressure. And without pressure, the liquid water disappeared. And without water, everything disappeared. Mars is a planet that died from the inside, from the core. But before you decide we've found the big secret, I have to tell you something that videos about magnetic fields usually gloss over. Venus also has essentially no magnetic field, no internally generated dynamo, yet it has an atmosphere, one so thick that Earth's looks like a vacuum by comparison. So, no field, no atmosphere is too simple. It doesn't work as a universal rule, and anyone who presents it to you that way is oversimplifying. And when you start to dig into why Venus kept its atmosphere but lost its water, something more subtle comes to light, and more frightening. Venus managed to hold on to its atmosphere, largely because of its mass. It's almost Earth's twin in size and gravity, and its dense carbon dioxide is kept in place by gravity. But it lost its water, and it lost it exactly the way planets lose water when they have no working shield and no working thermostat. At some point, Venus probably had water, maybe even oceans, but Venus is closer to the Sun, getting nearly twice as much energy as Earth. Water evaporated, water vapor rose high into the atmosphere, and water vapor itself is a powerful greenhouse gas. It trapped heat, it got hotter, more water evaporated, the vapor rose even higher, a self-reinforcing feedback loop. And up high, where that vapor reached, the Sun's ultraviolet light split water molecules into hydrogen and oxygen. The lightweight hydrogen escaped into space space forever. And that's how, molecule by molecule, the planet dried out, not blown away by solar wind like Mars, but simply evaporated and broken apart from above. This is called the runaway greenhouse effect, and here's why it matters. Venus shows us that you can keep your mass, keep your atmosphere, even keep your carbon dioxide, and still turn into a dead hell if you don't have a mechanism that regulates temperature. If there's no one to hit the brakes. But Earth has such a mechanism, and it's probably the most underrated thing in the entire history of our planet. No one makes videos about it. It has a boring name, but it's the thing that has kept Earth alive for 4 billion years, and it's not listed in any exoplanet search catalog. That mechanism is plate tectonics. Here's the thing. Earth is the only known body in the solar system whose crust is broken into plates, and those plates move. Not figuratively, they literally crawl, at about the speed your fingernails grow, a few centimeters a year. In some places, they pull apart, and mantle material rises up to form new crust. In other places, they collide, and one plate slides under another, sinking back into the mantle. This process is called subduction. Mars doesn't have that. Venus doesn't have that. As far as we can tell, its crust is one solid piece, like a lid, and it periodically seems to flip over through massive volcanic catastrophes. But there are no plates in the Earth sense. Only Earth split into pieces and breathes through them. And this breathing, that's the break that Venus was missing. Here's how it works. There's carbon dioxide in the atmosphere, a greenhouse gas that traps heat. Rain washes some of that CO2 out of the air. Water reacts with rocks. The carbon gets locked away and eventually ends up on the ocean floor as sediment, as carbonate. Then that carbon, along with the oceanic plate, slides into a subduction zone and goes back down into the mantle. And then, millions of years later, volcanoes release it back into the atmosphere. The circle is complete. Now, here's the beautiful part. This circle self-regulates. The planet gets too hot, more evaporation, more rain. CO2 gets washed out faster. The greenhouse effect weakens. The planet cools down. Gets too cold? Less rain. CO2 weathers more slowly, but volcanoes keep pumping it out. It builds up in the atmosphere. The greenhouse effect strengthens. The planet warms back up. This is a thermostat, a real planetary thermostat running on continental movement. It reacts slowly, over hundreds of thousands and millions of years, but it does react. And that's exactly why, for 4 billion years on Earth, despite the young sun shining noticeably dimmer and then gradually brightening, the temperature has stayed within a corridor suitable for liquid water. Think about how incredible this is. The sun's luminosity increased by about 30% over this time. 30%? That's colossal. Yet Earth remained with its liquid oceans. Because the thermostat dialed the greenhouse effect in the opposite direction, compensating. Venus lost this break, or maybe never really had it, and it drifted into the hot side, irretrievably. Mars is too small. It cooled down. Its thermostat stalled in the cold direction. But Earth holds on, between two abysses, on a narrow ridge, for 4 billion years. And now bring this back to our table. Can a telescope determine if plate tectonics exists on an exoplanet? No, not at all. It's impossible to measure from hundreds of light years away with any instruments we have or will have in the foreseeable future. We don't even know how common plate tectonics is as a phenomenon. Maybe it's very rare. Maybe it requires a perfect alignment of conditions, the right amount of water for lubrication, the right mantle temperature, the right composition. We don't know. But if tectonics is rare, then planets with a working thermostat in the galaxy are far fewer than planets of the right size in the right zone. And without a thermostat, a planet is Venus or Mars. It's just a question of which way it will drift. And note, we're still only talking about having stable liquid water on a planet. We haven't even gotten to life yet. We've been building the set for 4 billion years. The moon, the core, the field, the plates, the thermostat, and the stage is still empty. Not a single living thing. Time to fix that. And this is where, perhaps, the most insane part of the whole story begins. Because the first thing life did, once it appeared on Earth, was nearly destroy both itself and the entire planet. Let's rewind to about the 2.5 billion year mark. By this point, life on Earth already exists, but it's simple, unicellular, microbes in the ocean. And the planet's atmosphere is completely different from today. There's almost no free oxygen. You couldn't breathe this air. You'd suffocate in minutes. The sky might have been a different color. The oceans, saturated with dissolved iron, might have been greenish. And then, in this world, cyanobacteria appear, tiny organisms that mastered a new trick, photosynthesis of the type that uses water and releases oxygen. They take sunlight, carbon dioxide, water, and produce energy for themselves and throw away oxygen as waste. Like trash, oxygen for them is a byproduct, exhaust. At first, this oxygen didn't go anywhere into the atmosphere. It was greedily absorbed by that same dissolved iron in the oceans. Oxygen bonded with iron. The iron oxidized, simply rusted, and settled to the bottom. Whole layers. They are still found all over the world, banded iron formations, a layered cake of oxidized iron on the floor of ancient seas. A significant portion of the iron ore that humanity mines today and uses to make everything is the rust from that era. The trash that cyanobacteria produced billions of years ago. But then the iron ran out. There was a lot of it, but not an infinite amount. And once the oceans were saturated, oxygen had nowhere left to go except into the atmosphere. So it shot straight up. That event is called the Oxygen Catastrophe, or the Great Oxidation Event. And the word catastrophe isn't just for dramatic effect. You see, for most organisms back then, oxygen was poison. Genuine, deadly poison. Those microbes evolved in a world without oxygen. Their biochemistry wasn't built to handle it. Oxygen is a chemically aggressive element. It oxidizes things. It tears apart cellular structures. And now this poison was building up everywhere, in the air and in the water. In all likelihood, this was the single biggest mass extinction in Earth's history, long before the dinosaurs, long before any animals. A massive chunk of the biosphere was wiped out by the waste product of just one type of bacteria. Life itself, by its own hand, had flooded the planet with poison. But that's not all. Oxygen didn't just hit the planet directly as a poison, it also hit the climate, and that's where the scale becomes truly planetary. Back then, the ancient atmosphere was full of methane, a powerful greenhouse gas, way stronger than carbon dioxide. It kept the young Earth warm during a time when the sun was dimmer, and into this warm, methane-blanketed world, oxygen flooded in. Oxygen reacts with methane, breaks it down, turns it into carbon dioxide and water. That greenhouse blanket that kept the planet warm literally fell apart chemically, and Earth froze, not just partially. According to one leading hypothesis, the planet iced over almost entirely from pole to equator. Glaciers crept down to the tropics. The oceans were capped in ice. This model is called Snowball Earth. The planet turned into a white ball, reflecting sunlight back into space, and the more ice, the more reflection. The colder, the more ice. Another self-reinforcing loop, this time spiraling toward deadly cold. Let that sink in. Life appeared, invented photosynthesis, poisoned its own atmosphere with its waste, triggered the biggest extinction event, and on top of that, crashed the climate and froze the whole planet into a block of ice. All of that from a single biochemical trick mastered by microbes. If you'd been watching Earth from the outside at that moment, you'd probably have written it off. A planet where life emerged and immediately started killing itself. A frozen white ball. End of experiment. But now, the twist I've been building up to. That same oxygen, the poisonous waste that destroyed the ancient biosphere and froze the planet, is what you're breathing right now. Every breath you take, 21% of the air around you is a poison that life didn't just eventually adapt to, it built everything that came after on top of it. Because oxygen has a quality that makes it priceless if you learn to handle it. It gives energy, a lot of energy. Breathing oxygen, what your cells are doing right now, yields many times more energy from the same food than any oxygen-free method. And this energy revolution, this access to a rich power source, ultimately opened the door to large, complex, active organisms, to animals, to brains, to you. Poison became fuel. Catastrophe became foundation. The worst thing that ever happened to life on Earth turned out to be the prerequisite for everything interesting that followed. And that, by the way, is the theme of our whole story. You've probably noticed by now. The collision that should have destroyed the planet gave it the moon and its core. The poisoning that should have killed life gave it the energy for complexity. Over and over, catastrophe becomes foundation. Not because it was designed that way, but because you and I are sitting on the one branch where all these catastrophes accidentally turned out right. On every other branch, there's no one around to do the counting. All right, oxygen is here, energy is here. You'd think complex life would just take off on its own, right? No, because between a bacterium and you, there's a gap that life, as far as we can tell, jumped across exactly once in Earth's entire history. Look, all living organisms fall into two camps. There are prokaryotes, bacteria and similar simple cells without a nucleus, tiny, built in a pretty basic way. They ruled the planet for billions of years. And then there are eukaryotes, cells with a nucleus, complex, large, with internal structure. Everything you can see with your eyes is made of eukaryotes, plants, fungi, animals, you yourself. Every cell in your body is eukaryotic. Now, the jump from a simple cell to a complex one isn't a smooth, gradual ladder. It looks like one specific, incredible, almost impossible event. About 1.5 to 2 billion years ago, one simple cell somehow ended up inside another, and it didn't get digested. It didn't die. It just stayed there, living. One cell inside another, and they started working together. Over time, the inner one turned into an organelle, a mitochondrion, a tiny power station that still sits in every one of your cells, churning out energy using that very same oxygen. Right now, inside your body, there are trillions of descendants of that engulfed cell. Mitochondria even have their own little DNA, separate from yours, a trace that they were once independent organisms. And here's the key point. As far as we can tell, this symbiosis, this fusion of two cells into one, happened only once in the entire history of life on Earth. One time. All eukaryotes, all the multicellular diversity of the planet, all plants and animals, all humans, were all descendants of that single event. One meeting of two microbes that somehow didn't end with one just eating the other. This might explain something strange. Life on Earth emerged fast, almost as soon as the planet cooled down enough to make it possible. But complex life took billions of years to show up. Simple cells appeared almost instantly, while complex cells came halfway through the planet's entire history. It's as if the origin of life is a relatively easy step, but turning it into something complex, that's the real filter, the narrow bottleneck that almost nothing gets through. And this, by the way, is one possible answer to why we still haven't heard from anyone out in the galaxy. Maybe simple microbial life is scattered across the cosmos in abundance, but that one, improbable, random leap to a complex cell, most planets never make it. They remain worlds where oceans teem with bacteria for billions of years, and nothing more complex ever emerges. Stick that in your search matrix. Column: did life on this planet make the incredible one-time symbiotic leap to a complex cell? How do you measure that from a light curve? You don't. It's not measurable at all. Okay, let's say you got lucky. The planet is right. There's a moon, a magnetic field, a thermostat that works, oxygen built up, the complex cell was born. Smooth sailing from here, right? Wrong again. Because what follows is a series of attempts to wipe it all out. And there were at least 5 of them. They're called mass extinctions, the Big Five. Moments in Earth's history when not just a few species died off, but a colossal fraction of all life on the planet disappeared in a geologically short time. The first one, at the end of the Ordovician period, about 440 million years ago, roughly 85% of species went extinct, linked to a sudden glaciation. The second, the Devonian, a drawn-out series of extinctions, again massive losses, especially in the oceans. Third, the most terrifying of them all, the end of the Permian period, around 252 million years ago. It's known as the Great Dying. Estimates say up to 96% of all marine species perished. 96%. Life on the planet was literally a hair's breadth away from total reset. The main culprit is thought to be catastrophic volcanic eruptions, the so-called Siberian traps, which flooded an area the size of a continent with lava and poisoned the atmosphere. The fourth, at the boundary between the Triassic and Jurassic, it cleared the stage and, in many ways, paved the way for the dinosaurs. And the fifth, the famous one. Around 66 million years ago, the Cretaceous-Paleogene extinction event. You've definitely heard about the fifth mass extinction. That's when the dinosaurs disappeared. Well, not all of them, to be precise. Birds are the surviving descendants of dinosaurs, hopping around outside your window right now. But the giant non-avian dinosaurs that had ruled for over 150 million years, they were gone, almost entirely. Today, we're pretty certain about the cause. An asteroid roughly 10 kilometers wide slammed into Earth. We've even found the impact site, the Chicxulub crater on the Yucatan Peninsula in Mexico, over 150 kilometers across, buried under younger layers of sediment. The energy released was unimaginable. Thousands of cubic kilometers of rock were blasted upward. Tsunamis swept across the planet, and so much dust and soot filled the atmosphere that the sky darkened for months, maybe years. Photosynthesis slowed, plants died, food chains collapsed from bottom to top. Cold, darkness, starvation. And here's where it takes that same turn we keep coming back to in this story. While dinosaurs roamed the planet, mammals were already around for tens of millions of years. But they were small, nocturnal. They hid, scurried beneath the giants' feet, kept their heads down. They didn't stand a chance of moving up the food chain while dinosaurs held the stage. Then the asteroid hit and wiped the dinosaurs out, cleared the stage. And into that emptied world stepped those same small mammals. They started growing, branching out, filling the vacant niches. Eventually, primates emerged from that line. And from one branch of primates, we came. If that asteroid had missed, and it could have missed, it was pure chance, a matter of minutes in the motion of celestial bodies. Dinosaurs might still be ruling today, and our ancestors would have stayed as small, nocturnal creatures. You wouldn't exist. There would be no one to look for a second Earth, because the first intelligent species that thought to search for it would never have appeared. You see where I'm going with this? Our history isn't a smooth climb up a ladder from simple to complex. It's an obstacle course littered with near misses. 5 times, life on this planet nearly ended. And each time, just enough survivors were left to start over. And each time, the wreckage of the old world became the foundation for the new one. Remove any one of those extinctions, and the next floor never gets built. If the Permian extinction had been just a bit more complete, if it had reached 100%, that's it, an empty planet. If the asteroid had missed the dinosaurs, reptiles would still be on top. We are not the crowning achievement of an inevitable process. We are what was left at the bottom after the planet got shaken up 5 times and half of it was dumped out. We're a winning ticket, but you only know it's a winning ticket after the fact, once you're already born. Now let's put it all together. The entire list of things that had to line up. The right star, stable, calm, long-lived. The right distance. The right planet size to hold an atmosphere, but not accrete a hydrogen envelope. A giant impact at the right moment, at the right angle, giving it an anomalously large moon. A moon that stabilizes the axis. A core that hasn't cooled off, maintaining a magnetic field. Plate tectonics, possibly rare, acting as a thermostat, keeping the climate on a narrow ridge between Venus and Mars for 4 billion years. Enough water, but not too much. The emergence of life. The oxygen revolution, and surviving it. That one, probably irreproducible symbiosis that gave rise to the complex cell. And 5 mass extinctions, each nearly wiping everything out, but each clearing the way forward, including the last one, which removed the dinosaurs and let us take the stage. Now the question, how much of that list can we actually spot on a planet hundreds of light years from Earth? Virtually none of it. Let's be honest, no sugarcoating about what our telescopes can really do. Take the best we have, the James Webb Space Telescope. When an exoplanet passes in front of its star, a sliver of starlight filters through its atmosphere, if it has one. Different gases absorb light at different wavelengths, leaving narrow dips in the spectrum, like a barcode. From that barcode, in principle, you can identify some gases in the atmosphere. That's a fantastic achievement, working out the air composition of a planet you can't even see as a dot tens of light years away from the slightly distorted light of a distant star. It's borderline magic. I take my hat off to the people who figured this out. But let's understand the limits. This works reliably, mostly for large, hot planets with puffy atmospheres. For a small, rocky, Earth-like planet in the habitable zone, it's at the very edge of what's possible, and often beyond it. And even when we do catch something, we get a handful of gases. Not the moon, not tectonics, not the history, not the core, not whether the planet had 5 mass extinctions. A few molecules in the air, that's it. And here's a living example, fresh off the press, of how this plays out in reality. Planet K2-18b. Headlines exploded, possible signs of life, a biosignature, a molecule that on Earth is produced mainly by living organisms. The exact same headlines as 20 years ago with Gliese. Maybe we're not alone. But what's really going on? Really, it's a planet several times more massive than Earth, and scientists are still debating even the basics, what it actually is, whether there's an ocean under a hydrogen atmosphere, or whether it's a completely different type of world. The detection of that famous molecule is statistically shaky, barely above the significance threshold, and other teams rechecking the data find a much weaker signal or none at all. And as it turns out, the molecule itself could have non-biological sources. So, even in the best-case scenario, where they aimed the best telescope at a promising target, we didn't get a discovery of life. We got another debate about whether we read the barcode right. And this isn't because scientists are doing a bad job. On the contrary, they're brilliant. It's because the task is that hard. We're trying to reconstruct, from a few molecules in someone else's air, something it took Earth 4.5 billion years of unique events to build. It's like trying to understand an entire human life. Every decision, every person you've loved, every loss, every twist of fate, from a single blurry photo taken from the other end of the city. You'll make out something, a silhouette, maybe the color of their clothes. But a life isn't a silhouette, and a planet isn't a barcode. So let's go back to the very beginning, to that list of 9 second Earths we started with. Gliese, the Keplers, TRAPPIST, Proxima. Now you see them differently, right? They aren't Earth's twins, they're dots. Dots that happen to be the right size at the right distance, meaning they check exactly 2 boxes out of that enormous list we just went through. 2 check marks out of a couple dozen. And for everything else, we know nothing about them, and honestly, we won't in any foreseeable future. Calling them a second Earth is like finding a car in a parking lot that's the same make and color as yours and declaring you found your car. With all the scratches, everything in the glove compartment, every road trip it's ever been on. No, you found a similar silhouette. That's it. So, is it all sad then? Are we doomed to loneliness? But here's where I really need you to understand me. This video isn't about exoplanet hunting being pointless. It's not pointless. It's one of humanity's greatest projects ever. Finding these worlds, studying their atmospheres, debating about molecules. That's beautiful, and we should keep doing it. This video is about us asking the wrong question. We ask, where's the second Earth? And set ourselves up for endless disappointment. Because we're looking for an object that isn't an object, it's a process. We're looking for the result, forgetting that the result can't exist without the entire journey that led to it. Earth isn't a place with certain parameters. Earth is a route. One specific route, 4.5 billion years long, traveled without a single fatal breakdown. And even if there's a planet in the galaxy that took a similar route, it took its route, not ours. With its own Theia, its own mass extinctions, its own chance events. It won't be a second Earth. It'll be a first itself. Maybe the real number of Earths in the universe equals the number of stories ever lived, and each one is utterly unique. So take a second, look away from the screen, and just look around you. The air you're breathing, That's recycled poison from ancient bacteria. The stable seasons outside your window? That's a gift from a planet that smashed into the young Earth. Your body is made of cells, each one holding a descendant of a microbe swallowed 2 billion years ago. You yourself are someone who survived because one rock, 66 million years ago, hit instead of missed. We've spent 20 years and billions of dollars staring at distant points, hoping to find a second home. But the only habitable planet humanity has ever found has been under our feet the whole time. We already found it. We're standing on it. And there is no other exactly like it, and apparently there never will be. So maybe we should treat it a little more carefully. If you've made it this far, you're my kind of person, and I want to say thank you. Videos like this only thrive because of those who stick around to the very end, not just scroll past. Hit like if it gave you something to think about, and drop a comment letting me know which twist in this story surprised you the most. Theia, the great oxidation event, or that one unique symbiosis? I'm really curious. And if you want more deep dives like this, where we don't just rehash headlines but actually break down what's behind them, you know what to do with that subscribe button. See you next time.